Hello everyone. We're going to continue today. We're going to continue our discussion on lines and plane, and I'm hoping that today's video will be the last one. But we'll see. We'll see how long this one's going to go. But I don't have that much more to show you, and I'm going to try to squeeze into this video. So yesterday on the last video we talked about parametric representation of a line, and we're going over different ways to rewrite a parametric representation to an equation or equation to parametric representation. And one of the most important concepts that you have to get out of last video is that parametric representation they are not unique. As a matter of fact, they are kind of like describing the same object but using different movement to describe it. So the best way to actually think of it as just like what I said yesterday is not to think of it as the track that you're describing, but rather runner on the track. So you can have multiple runners who run at different speed, starting at different points on the track, but they all kind of follow the same track, which in this case the track is the line. So because of that, the parametric representation is not unique. And therefore, there are plenty different ways to actually generate a parametric representation of a line. So as you recall, from what we learned so far, we can write a parametric representation of a line using a direction and a point on the line. And if you think about it, it mirrors what you learned in geometry, where you learned that in geometry, if you have the slope and one point on the line, you can define the line. But that's usually not the first way students think of when they have to generate a line. As a matter of fact, the first way that most students think of to generate a line in geometry is a line is defined by 2 points. So therefore, it makes sense that we should be able to write a parametric representation of a line if we're given 2 points, because any line that goes through those 2 points will be unique. And therefore now we have a way to represent it. So that's what we're going to talk about today. So let's say we're given 2 position vectors. Let's say in this case vector A and vector B. Then the parametric representation of a line that contains these 2 points is given by the following formula. So remember, we basically just need a direction vector and a position vector to define the line. So how do we find that? Well, if we're given 2 position vector, you already learned in 1.2 how to form a direction vector between 2 position vector, and that is through subtraction. So therefore, the line, the parametric representation of the line will be vector x equal to t times vector b minus vector a plus vector a. So in this scenario right here, this vector b minus vector a is basically the direction vector from A to B. And then this basically become our position vector. So how did this mathematical expression work out? So remember, it's very important that you look at this expression right here and try to understand what it's telling you, because what we are learning in math is to learn how to describe something that we already know using a mathematical notation. And if you cannot do that, you won't be able to do math with it. So imagine the following. Imagine I have this one line. It really doesn't matter what the line looks like. So let's say here's my line. I'm going to go and try to describe this line. And what are we given would be these 2 points. And let's say here's where origin is. And then we're basically given these 2 position vector. Here's vector A. And here's vector B. And so now I'm going to try to describe this line. Now notice here's the important part. Notice that both vector A and vector B both identify a point on the line, which is what we need. But what it also need is a direction of the line that kind of tell me which way to go. So what we can do is to basically form that by forming this direction right here. And this direction is basically vector B minus vector A. That will allow me to now know which direction the line is. And now, I know some of you probably already thinking like, wait, but can I do vector A minus vector B? Wouldn't that work out exactly the same? And my answer to your question is absolutely, but there's a problem. As a matter of fact, this formula that I wrote for you on the right now is not the only formula when you try to write a parametric representation between 2 points, vector A and vector B. And no, it's not. And remember, are you surprised? No, you shouldn't be. Remember, parametric representation is not unique. So therefore, it now rests on the choice that we made. So in this particular formula, the choice that I made to present you this formula, I choose to look at the direction vector from A to B. And I choose to use point A as our point of reference. Those are my choice that lead to this particular formula. There are technically 3 other variations of this formula you can use, depending on whether you choose A or B as your point of reference, depend on whether you choose the direction vector from A to B or from B to A as your point of reference. Okay, and those are all valid choices. And nothing prevents you from using any of those 3 choices. Or are those 3 choices wrong? No, they are all correct. So with that being said, I do want to point out one thing. When I give you a task where you have to write the parametric representation of a line between 2 points A and B, I am going to ask all of you to use this formula right here. The reason, so that all of you will have the same exact parametric representation. Instead of, I have potentially 10, 20, 30 different parametric representations that they're all correct, and then I have to verify each and every single one of them. So keep that in mind. I want all of you to use this one formula right here. When you're given 2 position vector in a problem and you have to use this formula, if the 2 position vector label A and B, then just use them as A and B. If they are not labeled, then you can label the first one to be A and the second one to be B. So that way your formula will be consistent. And very important, why? Because when I give you a test and I look at this particular question, I will now know which one of you watched the video and pay attention to what I told you. Every year, I mentioned this 20,000 times to my student, like, use this formula, that's what I want you to use. Everyone should use this formula. And I always have at least a couple of kids, or sometimes more, who don't listen, don't pay attention, and just use a different formula. And then, now all of a sudden, you just tell your math teacher you don't pay attention in class. That is not a good thing. All right? So keep that in mind. Now, show you an example so that you can see how that works. Oops. All right. I don't know what happened here. All right, there you go. Show you an example and see how that works. So suppose I give you this problem right here. Imagine for following. Suppose, let's say I'm going to ask you to write the parametric representation of a line that contains the point, let's say 1, 2, 0, 5, and -3, 4, 1, 1. So now before we do anything, my first question, what dimension is this line in? So here's the thing. You can pause the video and think about it. Okay. How do I know what dimension is in? Simple. You look at the two vectors given. The two vectors given are both in R4. How do I know they're in R4? There are 4 numbers inside. Okay, if they have more numbers that are 0, I have to write them. So therefore, the fact that they have only 4 numbers tell me they have to be in R4. So because these two vectors are in R4, that would mean that the line that we're writing must also be in R4. Okay, so we are basically representing a line in R4. How does R4, like a 4-dimensional space, look like? I have no idea. As a matter of fact, most people don't have any idea either, because most of us cannot imagine how to put 4 different directions perpendicular to each other. Okay, because we can only visualize 3 directions in perpendicular to each other. That would be like the room that you're in. But we not care about that. We don't need to know how to visually see what R4 look like. As long as we know that it's 4 variable, that means R4, we're good enough. So how do I write this? So here's the important part. The problem specifies that both of these are points. So therefore, we are not given a direction vector. And you cannot use any one of these two to be the direction vector, because they're not. They are the vector right here. They are this one and this one, which neither of them go on the line. So therefore, mathematically, you can't use them in direction vector. So how do I go about doing this problem? Well, simple. I'm going to start by finding my direction vector. So how do I do that? So as I told you, if you're given just 2 position vector without any labeling, you can call the first one A, the second one B. There you go. So now I can use the formula. So my direction vector should be vector B minus vector A. So therefore it will be -3, 4, 1, 1 minus 1, 2, 0, 5. If you do your math correctly, remember this just requires you to do 4 addition or subtraction. And that's it. It's no different than what you have done since I don't know, first grade or something, when you first learn about addition and subtraction. So -3 minus 1 is -4. 4 minus 2 is 2. 1 minus 0 is 1. And 1 minus 5 is -4. So that will be my direction vector. My position vector, we will simply just use A to be my position vector, which is 1, 2, 0, 5. And so if you do it correctly, this is what your answer will look like. And some of you might ask, can I write it vertically like what we did before? Absolutely, yes. I just choose to write horizontal in this case, just to save room, so that way it won't like look too cluttered. But if you want to write vertically, you can. And then I guess the follow-up question is, can I always just choose to write horizontal or vertically? And my answer is, for the most part, until we get to chapter 2. Then we're going to have to talk about, like, should I write horizontal or vertically? And then eventually when you get to chapter 4, I'm going to kind of ask you to try to write it a specific way so that it help you understand what you're doing in chapter 4 and chapter 5. So we'll get to those, okay? So this is my answer. Now, if you follow the procedure correctly and use the correct formula, you should get the same exact answer. If you get a different answer, you're not listening. You didn't listen to what I told you to do. That's why you get a different answer. It's not wrong. Okay, but just not what I prefer. Okay? So keep that in mind. Questions so far? I think we're all good. So now the next question I want you to try to figure out is the following. So this question, I'm going to go ahead and state this question, and we're going to go over it in class. So when we talk about this video during class, sometime I might get caught up with explaining with you guys some other things. If that's the case, please one of you remind me that we have to go over this example together, because I want to make sure that you understand what to do with this example. You will see a question similar to this on your next test. So let's say given 2 parametric representations of 2 lines. One of them is vector x equal to t multiplied by -3, 0, 1 plus 0, 1, 2. And x equal to t 2, negative 1, 1, plus 1, 2, 0. So question is, are they parallel to each other? Do they intercept each other? And if so, can we find the intersection? Okay. Now, something very important here that I want to point out. Okay. Number one, we have two lines, but what dimension are we in? We're actually in R3 because both of these parametric representation, all the vectors are in R3. Okay. Good. Now, we already talked about how to determine their parallel, so I'm going to let you try to figure it out. But what I want to talk to you about a little bit would be, do they intercept? So this is where I want you to kind of figure out how to do that on your own. And if you and we'll go over it in class because it's very important. So I don't want you to just try to figure it out. And you might think you did, but then you're actually doing it wrong, and don't want that to happen. So we will definitely go over this problem in class. So if I get caught up with explaining something else, please make sure you remind me to go over this example because it's important. So, have you found intersection between two lines before? Absolutely, you have. You learned it back in I would say algebra 1. And the difference are the following. There's several differences that I want to point out, and then we're going to move on to something else. The first is the following. When you try to find intersection back in algebra 1, you are finding intersection between two lines on the xy plane. And guess what? Any two non-parallel lines on the xy plane, they must intercept at one point. So therefore, you know the intersection exists. Plain and simple. Unless they're parallel. If they're parallel, they either don't have intersection or they're the same line. But if they're not parallel, they guarantee to intercept. Now is a little different here. The reason why it's a little different here because of the following. We are in R3. So now think back in something you learned in geometry. Concept is the same. If you have two lines that parallel in R3, they don't intercept each other. That's pretty much true. Unless they are the same line, then they intercept everywhere. But in R3, it's also possible for two lines to not be parallel and not intercept each other. Those lines are called skewer. That means that two lines that not parallel to each other, but they don't intercept each other. And if you think about like, how is that possible? Well, in R3, it's entirely possible because imagine you walking along a straight line in second floor of the school while someone walking in another straight line not parallel to yours on first floor. You two would never run into each other. Your path would never cross. That's how it works. That's what skewer means. So in this case, these two lines, even if you find out, oh, they're not parallel from the first question, it doesn't necessarily mean that they intercept each other. Okay? It means that they could, but they might not, because they could be skewer. So keep that in mind. Number two, which is the important part, okay? And that would be the following. When we try to find intersection before, when you learn in 6th grade, you use the standard equation. And you know how to do that. So can we do that here? Can I rewrite this two parametric representation into like equation form and then just solve it that way? The answer is no. Why not? Because mathematically it is impossible to do. Okay, let me repeat. Mathematically, it is impossible to do. Why? Recall from yesterday. An equation form of a line can only represent an equation in R2. Guess what dimension we're working with right now? R3. Okay? So you will not be able to rewrite this into a line, and whatever line equation of a line that you think you come up with is mathematically incorrect always. Okay, so you cannot do that. So now the question comes down to, can I somehow find the intersection using these two parametric representation? And most likely a lot of students would do the wrong thing, but I do want you to try to figure it out first, some way to do it. And there are actually ways to go around it, because you want to show that they intercept, you only need to show that they share one point in common. So, and sometimes you can actually do that by just simply try and error. Okay, so I'm curious to see how some of you would do it, and I'll explain to you what happened and point out some very common mistake that you might have made while you're doing this. So hopefully that will leave a big impact on you. All right, so I'm going to leave that problem for you. However, if you want to know whether you do it correctly, you could check the notes from Google Classroom. I did the same exact example in the notes, so you can do that, but I would strongly recommend don't do that. So the last thing I want to show you is this. The last thing I want to show you will be this. I mean, the section is called lines and planes. So we talk a lot about lines right now. So finally we get to talk about plane. So what is a plane? Well, a plane, technically speaking, from our perspective right now, we'll talk about it slightly differently later. But for now, the plane is basically a geometrical object that's kind of like the piece of paper that you have on your desk. It's flat, two-dimensional, and the difference between the plane and the paper that you have is that a plane, it's infinitely large, so it's not like have boundary or anything, but beyond that, that's what a plane is. And you learn that in geometry. You have learned, yes, you find out that a lot of times when we talk about things, I always refer to things that you have learned already, because that's how it is. We're expanding what you already know, and we're expanding the knowledge that you already possess into higher dimension, in a sense. So you have learned that any two intersecting lines, well, intersecting and non-parallel, intersecting line, non-parallel, because technically speaking, if you have two intersecting and parallel lines, they are just one line, so you can't use it. We have learned that any two intersecting lines, non-parallel, intersecting line, define a plane. And so what we're going to try to do is try to come up with a parametric representation for it. So how do we do that? Now, this concept is not new. You already learned this. As a matter of fact, you've been using it since Algebra 1. Yes, you have. If you remember, every time you draw XY plane, you draw the x-axis and the y-axis. That's what you're doing. You draw two intersecting lines, and you use that to define the entire XY plane. That's basically what we're doing. But of course, what we're going to try to do now is try to come up with a parametric representation of it. So how do we do that? Well, it's actually simple. We use what we know. So this problem says that we have to have two intersecting lines. So what I'm going to do, I'm going to go and draw myself two intersecting lines. Here, I'm going to call this one line number 1. And I'm going to call this one line number 2. And if you want to, you can basically draw these two lines as the horizontal and vertical axis, and that's perfectly fine because it's basically the same thing. That's basically what we're doing, drawing two intersecting lines. The reason why I purposely draw it like mine, line X, because I want you to understand that these two lines doesn't need to be perpendicular to do it. It just have to be intersecting and can be the same line. That's all. So now, how do I describe these two lines in a parametric representation? Well, simple. I need a point and a direction. So how about I do the following? For line 1, I'm going to define this one point, the intersection point. And let's say this is my direction. So I'm going to call this direction vector U1 to indicate the direction of line number 1. And we'll call this point vector v. And notice I didn't put a subscript underneath it because I intend to use the same point for line 2. So therefore it doesn't matter. Okay? And then I'm going to define a second direction. So this one will be the given point. I'm going to define a second direction. Maybe I do a second direction like this way. So this I'm going to call it vector u2, and this will be the direction of line number 2. So with that, I can now define line 1 and line 2 parametrically. So line 1 will be equal to vector x equal to t vector u1 plus v vector v. But because this is for line 1, I'm going to go and specify that the perimeter is only for line 1 because line 2 could have a different perimeter. Line 2 will be x equal to t2 vector u2 plus v2. So that would be u1, line 1 and line 2. So now the question is, if I combine these two things together, I get to form a plane. So what would the parametric representation of the plane going to be? Well, it's simple. The idea is that when I try to describe a plane, I have to describe every single point on the plane, which is vector x. And in this case, I can actually travel along either the first line or second line, which basically tell me that I can start from this one point right here, which is v, and then go in either the direction from line 1 or the direction from line 2. And here's the important part, because I'm allowed to travel in 2 different directions, that's the reason why it's the dimension 2. Okay, that's the reason why I call it dimension 2. So the dimension is directly relating to the number of directions that we can travel. And forward and back consider one direction. So in this case, I can travel line 1 direction or line 2 direction. So 2 direction, that means this is now 2-dimensional. So how to write out the plane parametric representation is just this. Vector x equals t1 vector u1 plus t2 vector u2 plus vector v. In this case, vector x would have to be in at least R3, which would mean vector x is x, y, z, or generically in Rn, which then we'll use the subscript notation and say it's x1, x2 to xn. We do not want to represent a plane in R2 because that will represent the entire R2 planes. So we don't do that. Okay, it's like talk about a line in R1. Well, in R1, the entire line is R1. So we don't really want to talk about that. In this expression right here, notice that T1 and T2, they are our parameters. Because we have 2 different directions that we allow to go, we must have 2 parameters. As a matter of fact, that is a signature. 2 parameters indicate that you have something 2-dimensional, and therefore indicate that in this case, if it's in this form, it indicates that you have a plane. And we now have 2 direction vectors because we have 2 directions that we can travel, but there's still only 1 single position vector. Because we need that single position vector to define a position where the plane is. Just because we have more direction vector doesn't mean we have more position vector, because I still need only 1 position to tell me where it is. Okay, so that 1 position, it can't tell me like relatively to the origin where this plane should be. And we only need 1 of them to tell me that. And then the direction, number of direction would indicate what the dimension of the object is. So with 2 direction vectors, we now have a plane. Okay, now something very important is the following, because we do need a non-parallel line. Something worth writing down for yourself is that you have to make sure that the 2 direction vector they cannot be multiples. What happens if they are? Well, if they are multiple, they are parallel. Then you don't have two intersecting lines. You have two parallel lines. Two parallel line does not. Two parallel intersecting lines, they do not form a plane. Okay? So the last two things I want to show you is the following. Is to first show you how to write a parametric representation of a plane and kind of show you, illustrate to you how they look like. Okay, so let's see. So of course the easiest type of problem from this is that I gave you everything you need to do it. So let's say I tell you this following. Let's say I'm going to ask you to write the parametric representation of a plane with, let's say, direction vector 1 0 0 and 0 1 0, and the plane, it contains the point 0 0 2. Then what is the parametric representation? Oh, in this case, very easy. The parametric representation will just be this. It will be t1 multiplied by first direction vector 1 0 0 plus t2 multiplied by second second direction vector 0 1 0 plus the position vector 0 0 2. That gives me the plane. Now here comes an interesting question. What does this plane look like? And that's what I'm going to ask you to think about and try to draw it, or try to think about what this plane represents, and then we can talk about it in class. Okay? So now the last thing I want to show you is this, and that will be the end of the video. I know it's a little long, but I'm just want to finish up this last thing so that way 1.3 is done. So the last thing I want to show you is this. So in geometry, you also learned that not only you can define a plane using two non-parallel intersecting lines, you also learned that three non-collinear points can also define a line, define a plane. So what does mean non-collinear? Meaning that they cannot be on a straight line. So if you have 3 points that don't line up perfectly, they will define a plane. So how do we form a parametric representation of a plane if you know there are 3 points on it? Well, simple. You do the same thing as what you would do with line. So if you're given, let's say, 3 position vectors of 3 non-collinear points. Let's say vector A, vector B, and vector C. Then the parametric representation of a plane that contains these 3 points is given by the formula. And once again, there are many variations of this particular formula. As a matter of fact, there are like 9 different variations, but I'm going to give you the variation that I want you to use. So the variation will be vector x equal to t1 vector C minus vector A plus t2 vector B minus vector A plus vector A. So in this expression right here is just like the line. Vector B minus vector A give us the direction vector from A to C. Vector B minus vector A give me the direction vector from A to B. And so if we start at A and go to both B and C, I will have the 2 direction vector as well as the position vector A. That's how I write the parametric representation of a line. And we'll give you an example. I'm also going to state the answer. So you can definitely try this problem and see if you get the right answer using this formula. So if you use a different variation of this formula, obviously you could get a different answer. And please don't try to figure out whether two planes are the same using parametric representation. That is something that we're going to have to talk about later on, and it's quite difficult to do. You cannot do it the same way as with lines, so please don't. But just simply use the formula I gave you here. So parametric representation of a plane that contains let's say 147, you can call that one A, -102, you can call this one B, and 055, you can call this one C. And if you do it correctly, you should have an answer. So I'm going to stop a little bit. If you want to pause the video now, you should, so they can do the problem and check your answers. Okay, so now I'm going to write out the answer. The correct answer is this. So hopefully you all get the same answer. If not, you can definitely ask me about it during class, or ask some of your classmates for help to see what they're doing. All right, so that concludes 1.3. So tomorrow we probably go talk more about this, and I very likely give you a class time, a day in class to work on your homework and try to ask more questions or catch up on the video. Okay, until I talk to you again, bye.